Okay, in this video we're going to explore limits a little further by looking at what we mean when we say a function is continuous. Now, pretty much every function you have dealt with and will deal with is continuous. And usually the intuitive idea behind continuity is that there are no jumps or sudden changes in the graph of the function. But we want to make this idea more precise. So we're going to choose a point on this graph. It's where the x value is 1 and the y value happens to be 2. And we want to think about what we mean when we say the function f is continuous at this point, where x equals 1. Again, the intuition, if you look at the graph, is that there are no jumps or sudden changes, meaning if I make a small change to the x value, the y value should also respond with a relatively small change. Another way to write this then would be to say that when x is close to 1, the y value, or f of x, is close to 2. On the graph, we could even say that as x values are sent towards 1, the y values should be getting closer and closer to the number 2. They don't suddenly jump all over the place. But that's exactly what it means then for the limit as x goes to 1 of f of x to be 2. So the key point here is that the function value, what you get when you substitute 1 into the function, has to agree with the limit as the x value approaches 1. So that close to 1, there are no surprises, there are no sudden jumps in the function value. So it becomes quite easy to generalize this. We pretty much say that a function is continuous at some value a in its domain if the limit as x approaches a is exactly equal to the function evaluated at a. To again illustrate what this equation means, the right-hand side here is just f of a. So on the graph, that's this exact point here we're looking at. The left-hand side is the limit as x approaches a of what the function value is. And that's pretty much asking for what happens to the function value when you look at a little tiny neighborhood around the point. And intuitively, the function is continuous at a point if whatever is happening at the point agrees with what is happening in that little neighborhood around the point. And so finally, we say the whole function f is continuous if, using the above definition, it is continuous at every single point in its domain. Okay, that last restriction is quite important, as we'll soon see. What we have said should be clearer if we look at some examples of how a function can fail to be continuous. Now, these guys can get quite wild, honestly, but the simple cases to keep in mind are as follows. We'll take the function defined by x squared almost everywhere, except when x equals 2, at which point we'll just declare that the input of 2 gives an output then of 6. So let's graph this. The curve is x squared almost everywhere, so that means we can just draw that curve first. Then we have the special case where x equals 2, so along this dotted line here. Normally, y would equal 4, because 2 squared is 4, but for this function, we're going to push this up to a y value of 6. And so, of course, we can write that f of 2, the y value at 2, should exactly be that 6. And so the intuition behind why this function fails to be continuous is that you're traveling along the curve nice and smooth, but then it suddenly jumps up here before continuing as before. That sudden jump is the discontinuity. And so to check how this fits with our definition using the limit, we should see what happens when we try and work out the limit as x goes to 2 and compare that with the value of f of 2. So to get the limit, we should be thinking about sliding towards x equals 2 from both directions and seeing what the y value approaches. And here you see that these pink arrows are sliding towards the hole, towards the y value of 4. So we'd have that the limit as x goes to 2 of f of x is 4. And so because this limit value of 4 disagrees with the function value of 6, because they don't equal each other, we'd say that this function is not continuous, it's discontinuous at x equals 2. Okay, so there's another type I want to quickly show you. So let's bring back an axis and we'll take another function defined in two separate cases again. Only this time, two different things are happening. The top case is when x is less than or equal to 1, and the bottom case is when x is strictly greater than 1. So obviously x equals 1 is a point of interest. It's like the boundary point between when the function behaves quite differently. To the left, we have this top case of x squared plus 1, and so we can draw our parabola shifted up by 1. And because the inequality includes equaling 1 in this case, we can pop a full circle at the boundary here. And so we have f of 1 equaling 1 squared plus 1, which is just 2. To the right, we have this bottom case of x plus 2. So we begin at the boundary where x equals 1, where the y value would be 1 plus 2, which is 3, but be careful, we don't take this point because this applies only where x is strictly greater than 1, so not when x equals 1, which is why we'd put an empty circle at this endpoint here. Then we just draw our diagonal line with gradient 1 and off it goes. Again, the fact that this function isn't continuous should be clear from the fact that the graph jumps at x equals 1, so that's no longer a surprise, but it's still worth noting precisely why, because this is a case we haven't actually seen before. Okay, so we've got f of 1 equaling 2 at that full circle we saw before, but when we're checking for continuity, we need to see whether or not this y value of 2 matches with the limit as x approaches 1. And so as usual, we can imagine trying to get this limit by sliding towards x equals 1 from both directions. From the left, we slide across the parabola like this, and so the y value it's clearly sliding towards is exactly this 2 here. Sometimes we can write this limit from the left like this, the limit as x goes to 1 minus, to mean as it goes to 1 from the negative direction. And so in this case, we have the y value sliding towards 2. But from the right, we need to slide across the straight line like this. So the y value is clearly sliding towards, well, 3 this time. Remember, for the purpose of the limit, we don't care what f of 1 actually equals. We only care what the y value is doing as we slide towards x equals 1. And as we do this from the right across the straight line, clearly the y value is sliding towards 3. And we can write this from the right as the limit as x goes to 1 plus. And so that means as it goes to 1 from the positive direction. And this time we get the y value sliding towards 3, as we said just then. So the crucial point here is that these two are different. From the left it's 2, but from the right it's 3. And so because they're different, the limit can't make up its mind. And so we say the limit just doesn't exist. It can't choose between 2 and 3, and so there's no sensible value we can give to the limit. And so we haven't actually mentioned this, but previously we said that for a function to be continuous at a point, the limit must agree with the function value, but actually a prerequisite for this, something that must be true even a step before this, is simply that the limit must exist. And in this case, the limit doesn't exist, and so there's your discontinuity at x equals 1. And so that's what makes a function continuous or discontinuous. We are checking that at every point in its domain, the function value agrees with the limit as x goes towards that value. And if that ever fails for any value of x in its domain, then the function is discontinuous. And so that's all for this one. Thanks for watching. See you around.